Hi, welcome to Teardown Tuesday with another Spectrum Analyzer, the Rigol DSA815 TG with the optional tracking generator. Thought we'd crack it open, take a look inside, because Spectrum Analyzers are usually a bit more interesting than other bits of test gear like your run-of-the-mill scope or your multimeter or whatever. Bit more engineering poured in these things. So, you know what we say here on the EEVblog, don't turn it on, take it apart. And here it is. You've seen it before in previous videos, and it's a real nice, solid design, real solid bit of kit. This one, I really like it. It weighs like 4.2 kilos. There's a lot of heft in this thing, which indicates a lot of shielding, maybe some die-cast stuff, of course, for the RF front end, perhaps. But it should be as easy to crack open as other Rigol gear is. A couple of screws here, a couple of screws up the top. The back will pop off, then we'll have big shielding at the, on the top half, the shielded power supply as well. That'll all pop open. We should be able to access the main board, but could be fairly involved in terms of getting the RF stuff apart and things like that. But I don't expect this to be a particularly like a high-end electronics as far as the RF goes. No fancy black magic stuff in terms of, you know, PCB, etched PCB filters and traps and things like that, because this only goes up to 1.5 gig. It's not, as far as RF spectrum analyzers are concerned, this thing is, you know, is pretty much a baby. It's basically working at DC as far as the RF engineers are concerned. And we have a sticker on top, demo equipment. Hey, we can fix that with a deft slice of the knife. There we go, no problems. And of course we have the obligatory warranty void sticker. And if other bits of Rigol gear are anything to go by, especially their new stuff, this should be pretty well designed and built. So, because they're really, well, they've always been quite reasonable in their construction, Rigol, but as of late, the new series of gear seems to be designed and engineered very, very well indeed. So I don't expect to see any shoddiness inside this thing. I expect really decent build quality and nice clean PCB, probably washed nicely, all that sort of jazz. All right, this puppy should just lift straight off. Maybe, if I've actually got all the damn screws out. Maybe not. There we go. Ta-da! And yeah, the obligatory metal shielded back on this thing. Power supply under here, and that'll also be shielded from the rest of the circuitry. And we've got a couple of headers down here. They're polarized with the missing pin there, so they're some sort of programming or test interface, something like that. Got the nice shielding down here in the Ethernet connector and the USB. You can see the shielded lugs there, really nice EMI shielding on that. And of course we've also got a little mount and shield for the mains connector there. Neat. And it looks like this whole thing is going to lift off rather than just this up here. So get our screwdriver under there. We can lever that whole thing off, and that power supply is going to come off in one section, and the obligatory big power cable going over. Oh, it looks nice in there. Looks nice. You'll see it in a second. Hold on to your hat. And here we have it, folks. Whoa, look at this. Beautiful. We've got the huge die-cast box we've got here for all the RF circuitry and all of this juicy stuff we've got under here. As you'd expect, we've got a Spartan 6 FPGA, and we'll go into details. We've got an Actel Pro ASIC 3 by the looks of it, some flash memory, and a Blackfin DSP processor down there, some power supplies up here, and interestingly, some a small little angled heatsink there with TO220 packages with some sill pads under there for isolation. And this, ta-da, check it out, they're a little bit proud of it. Design in China. Not designed in China, so yeah, right, good one. Chinglish. And we're actually looking at a version 1.05. Looks like the 30th of the 12th, 2011. And here we've got a fairly pedestrian, I guess you could call it, Spartan 6 FPGA. It's the XC6S LX25, and it's only like a 24,000 gate device, so it's not particularly high density at all, but it does have built-in almost 1 meg of RAM. So they're using this for the display processor. Clearly, here's the external memory as well, and you can tell it's essentially the display processor because, well, it's hooked into, you guessed it, the display connector down there, and you can see all the termination resistors on the bus there to drive the long cable off to the LCD. And once again, the bastards, look, they've put this magic tape or laser etch or whatever it is on this chip here like they've done in other ones. And this is, it looks like the ADC, because if you have a look here, there's this controlled impedance trace here running up through that via there, which probably comes out of the RF section here, runs over to here, down through a few choice inductors there, and through looks like there's a little, I don't know, is that some sort of little common mode transformer or something? I'm not sure, but that's probably the ADC, I would be assuming, with maybe some local voltage regulation here perhaps, and of course that flows parallel output bus flowing into the FPGA there, straight into the display FPGA processor. I mean, that FPGA is probably doing other stuff as well as the display processor. And they've gone to town on the silk screen here. They've identified all of these various differential pair lines in here. I mean, we've got D in, clock, we've got done, we've got TX in, TXP, sync negative, sync positive, RXP, init program, various lines there. Once again, directly coupled into that main Spartan 6 FPGA. So that's obviously the capture and processing as well as the display engine. And of course, that's got its own JTAG connector down in there, which they use to program this thing and or debug or do in-system tests or something like that. And there's that chip up close, and yep, it does appear to be laser etched off. You can almost see the lines going across the thing, and it is definitely like stepped down into it. So they've done something to really etch out the top of that chip. Bastards. Pretty darn effective though. And down closer towards the main processor, which is a Blackfin, I'll show you in a minute, we've got another FPGA. It's an Actel Pro ASIC 3, and it's rather interesting why they use you know, multiple vendor FPGAs in this thing. They obviously had a specific requirement based on cost or whatever, but they love to chop and change for various things here. Anyway, we've got a 64 megbit expansion flash memory. We've got a fast SRAM here, and up here we've got a Cypress USB microcontroller. And no surprises, of course, for finding a Blackfin DSP processor in here, same as what they use in the Rigol series scopes. Of course, you know, they've already got the development system, a lot of code, reuse it with the Blackfin processor. And next to it here, we have a Micrel Ethernet controller. It's a KSZ8051. So this thing actually has Ethernet built in, but they've decided to use an external Ethernet controller here. And this section here, just above the processor, they've got a Linear Technology LTC7328 LX two-phase synchronous regulator. And you can see above it, just there, you can see the two external MOSFETs as well, the two external N-channel MOSFETs used for the synchronous rectification. And it's probably wouldn't be a stretch to guess that they've got the switch-in frequency of this thing locked to the sampling frequency so that it doesn't interfere with the acquisition part of the RF front end. No surprises for finding a whole bunch of low dropout linear regulators here, you know, 1117s, you know, sort of like the industry standard. We've got 5-volt rails. They've got all sorts of little test points here. 15 volts, you go right over to here. We're talking 32 volts up here, and they've got various other rails, and they're all hooked into nice little test points all down here. Very well labeled board, very well laid out. Now there's one thing I'm not seeing around this part of the circuitry here. I mean, here's the 10 megahertz reference out, external 10 megahertz reference in, and you know, apart from a 32 kilohertz watch crystal up there for the time date, I don't see any obvious crystal oscillator module on this thing. In fact, I expect it to be a reasonable quality one, but I assume it must be on the bottom side of the board, because unless I'm blind, I can't see it on the top here. And if you're wondering what the TO220 devices are, well, sorry, nothing exciting, just a bunch of LM317s and 337s. So that's a very neatly presented and neatly laid out and well engineered main PCB there. I mean, it's going to extend under here. It's quite possibly the full width of this whole unit right under the die-cast shield here where the RS front end is. But yeah, it's, you know, it's super clean. There's no flux residue on here at all. Well laid out, well silk screen. It's got all the JTAG interfaces and various things. If you want to hack and play around with it, we've got our LCD connector down here. This will be our keyboard up here, I'm assuming. And well, looks like we're going to have to take this thing apart. Look at all the screws on there. So I'm not sure how this thing lifts out. I mean, there's a couple of screws on here for the main board, but I think if I just take those out, it's not just going to lift out. But then I'm not sure if I take out these ones first. Maybe there's a couple of them that hold it in down lower. Oh, I don't know. But you can bet your bottom dollar there's some porn under there. And here we go. That was an awful lot of screws, and there did seem to be 2 lengths here, which was rather annoying, so I only got to record a couple of them. But anyway, here we go. Let's lift the skirt. I expect to see some RF gasketing perhaps on the bottom of this. Oh, one big board. Oh no, there's no RF gasketing. Look, it's just directly like, you know, directly just the machined aluminium backing on that. Go figure. So yeah, anyway, this is a bottom of the range spectrum analyzer, so I guess you don't expect to get all that goodness, but oh, look at that. Once again, as with every RF spectrum analyzer, you'll get, oh, there's a couple of filters and stuff on the board. I was wrong. I was wrong. We'll take a look at these. I didn't expect to see well, much, if anything, in the way of PCB filters there, because this thing's only a 1.5 gig scope. But there you go. It's like, it's very modularized. I don't see any labels on the individual modules at this stage, but you know, if you know your RF spectrum analyzer, you know, the workings of it, the topology, the top level block diagrams, you could figure out what each section does. And I just popped out the main board, and that was really easy. I mean, it's there's nothing holding it in there at all once you do off all those top screws. And there's the matching shield for the bottom set of that, and of course the end connectors just pull straight out of there, and the board down here is completely integrated. It's really very nice. And look what we have here. We have another Xilinx Spartan down there, but we'll take a look at each section in a little bit more detail. I mean, geez, we could spend hours analyzing this thing. I mean, really. And is very typical of most products with these large hand-soldered BNC connectors. you see some flux residue around there on the board. Nothing major though. And let's see if we can follow this thing, shall we? Now, I'm not going to go into a full system breakdown of a spectrum analyzer and absolutely nail each module on the head. I'll leave that to the viewers. I'll be posting high-res photos on the site, by the way, so if you want to check out the board in some more detail, there should be some high-res photos there for you to play with. Now, here's our input, of course. Here's our end connector down here. Straight in. Now, when you're probing around these things, just be very careful about ESD, because there is some sensitive stuff on here which you really don't want to kill at all. So anyway, we've got our input there directly AC coupled straight in, hence the minimum bandwidth of this thing is 9 kilohertz, because, well, there's a series cap on the input. You can't measure down to DC on these things. These are not dynamic signal analyzers. They are RF spectrum analyzers. Straight in, we've obviously got some sort of buffer or something like that. Not sure what the other two chips are. Might have a look in more detail. And of course, all of this is controlled impedance stuff, as you know, and as I've talked about before. And also check out all the heavily stitched vias all the way around each individual module. Is each circuit, each system module is heavily via stitched, basically to lower the ground inductance, to ensure that the ground inductance in all places around the module is, well, it's basically DC. At RF, inductance is absolutely everything. So what have we got? We've got our input here. It doesn't look like there's any, there might be some attenuation happening in there, I'm not sure, but anyway, we're jumping through the wall here because there's a die-cast shield here. So this one, some of them go under, like this one here is jumping under. You can see the controlled impedance tracing there, goes through a via, then actually jumps under through a middle layer and back up through to the top side there. This one doesn't bother doing that. It goes straight across. I guess they wanted the minimum amount of loss there, because when you include a via like that, vias have inductance. So, you know, if you want the utmost in signal integrity, you try and keep everything on the top layer here. Now, if there's any components on the bottom side of the board of any note with each module, I'll tell you. Now, here's a chip. Once again, bastards have laser etched the number off there. Now, that possibly looks like some sort of input filter, maybe some attenuation, but those resistor values are all the same there by the looks of it. Then we've got some sort of amp, and then I'm not sure what's going on there. We're going into another. That's possibly, no, that might be the mixer, perhaps. Let me check the bottom side. And let's back up a little back to the input here. Check it out. TL072s. Hardly RF amps or anything like that, so they're just doing some very basic stuff with those TL072s. Nothing RF there at all. And then we go over into this network here, and yeah, they are all the same value resistors. Yep, they are. And then we jumping in, there's a low voltage there's a low dropout linear regulator on the other side of that. Just some local voltage regulation. Then we've got, looks like a multi-stage LC filter there, and going into another device, not sure what that one's doing there. And once again, they've lasered the number off that one. Bastards. So we're going into some sort of small network over to here, but over at this point is coming in from this filter here. So let's check that out. Now, this funny looking pattern etched onto the board here, this is just a multi element stub filter. Each one of those, like that big pad on the end of that, is actually acting as a capacitor, and then the trace going to it is actually acting as an inductor, depending on what size and shape you make them, based on the controlled impedance value and the distance to the ground plane underneath, and all that regular high-speed signal integrity stuff. So, you know, it might look like magic, but it's just a basic LC stub filter pretty much. And that's coming from this circuitry over here, I'm not sure what that's doing at all, but if you flip the board over, that circuitry, which is under there, actually, which is under around about there, comes from pretty much the FPGA on the bottom there. So looks like we've got our FPGA feeding this around here, which then jumps over to there, as we've looked at before, goes through this stub filter in here, through this controlled impedance trace, and then it drops down to the bottom, and it actually, I believe, it actually connects over to there, because I can't see anywhere else it would connect to. So it's jumping over there into there, which then mixes. So that might be the mixer, perhaps, and this might be something to do with the local oscillator, although it doesn't seem to be enough parts around there to do that. But anyway, it's going through another network up here, through another LC filter up here, and into another magic looking device over here. But this is nothing fancy at all. It's fairly common. It's just a bandpass filter, and once again, depending on the size and shape of the various traces on here, based on the thickness and type of material of the dielectric, etc., etc., this is just a multi-element bandpass filter. But as I said at the start, why they've done that on only a 1.5 gig bandwidth spectrum analyzer, I don't know, because you can see once again there's just a regular component multi-stage LC filter there going into another bandpass filter here, which why they didn't do that with regular parts at this sort of bandwidth, I don't know. You'd have to talk to the system designer about that one, I'm afraid. So this multi-element resonant stub filter here is really, you know, it looks kind of weird, but there you have a capacitor going to ground, essentially. Then you have another inductor here in series. Then you have another capacitor going to ground. Then you have another inductor here. And you can look at, there's an inductor there, there's a capacitor to ground, in this tiny little amount of inductance, capacitor to ground. And basically it's just a multi-element LC filter. Now I think I might actually have a bit of a bet that this section down here is the local oscillator next to the input there, and if I flip the board over, there's the base of it. Once again, got another lasered chip there, the bastards. So I think that's possibly the local oscillator there, once again going up into this, which then possibly goes and mixes up near the top somewhere, because if you know your spectrum analyzer topology, that's basically what you've got. You've got an input, and you'll have some sort of input attenuator, then you'll have some filtering, and then basically it goes into a mixer somewhere. So a mixer has to be up there somewhere, and then there's a local oscillator driving the mixer. So possibly local oscillator here, up there, driving the mixer, which is somewhere up there. I don't know. You could spend hours analyzing each one of these blocks and drawing the complete system diagram. You'll also notice some routed slots in there like that, and they've really went, well, we really don't want any coupling between those sections, so let's route out some slots. Good way to do it. And once we come out of that bandpass filter there, we go into another couple of blocks. There's some more filtering there, I'm assuming. We've got ourselves an RF relay there by the looks of it. And going over to some more filtering. I mean, there's bloody filtering everywhere on this thing. Everywhere you look, there's a whole bunch of LC filter. Hey, hello, check out that top inductor there. Oopsie, it's on an angle. Wah. So, you know, like there, look, there's another section of LC filtering. All right, I've got a basic block diagram of how a typical spectrum analyzer works here. Now, it's very simplistic. If you want to go into more details, there's plenty of info out there. Just Google it. You'll find how spectrum analyzers work in great detail, and this is going to be quite similar. So let's check it out. We've got our input here, goes into our input attenuator. So our input on the BNC, the N connector down here, input attenuator is going to be around here somewhere. There's going to be some you know, amplification and stuff like buffering and stuff like that. Our input filter is going to be, you know, around here somewhere. Then we've got a local oscillator, which I thought was down around here somewhere, and then it goes into a mixer, and that mixes the two signals together, and then that goes into a the resolution bandwidth filter, and you know, that is actually adjustable. So I'm not sure at what part bandwidth filter up there has anything to do with it. I don't know. It's in there somewhere, and it basically then pops out and goes into a traditional analog spectrum analyzer is going to have these additional stages as well. It's going to have an IF filter, adjustable IF filter, then it's going to have a logarithmic amplifier, it's going to have an envelope detector, then it's going to have a low pass video filter, and then goes into the ADC. But the DSA815 has basically doing all that in digital. So it's basically got a hide, so the ADC is connected directly to there like that, and it samples at high frequency, and it's able to do all this traditional stuff in as you know, computational stuff either inside the Spartan FPGA or inside the DSP processor itself. But all that is done digitally that you used to do analog in a spectrum analyzer. But you can see, I mean, you know, we've only got 5 basic blocks here for all this RF spectrum part, and you can see all, you know, there's like, you know, more than a dozen different blocks on there. So like this mixer, you can get multiple mixers and things like that. So, you know, there might be more than one mixer in there, and all sorts of additional filtering and control and all sorts of stuff. But anyway, that's just a very quick breakdown. I mean, if somebody wanted to go through, you could map out all the individual modules and how they fit in with your traditional RF spectrum analyzer front end like that. And by the way, this ADC here doesn't have to be a particularly high speed one. It's going to be a high precision one, but you know, the output of your resolution bandwidth filter and your mixer here is going to be, you know, in the order of tens of megahertz. So it's, you know, it's not like the ADC is put bandwidth of several gigahertz or something like that. It doesn't, because the local oscillator mixes that down to a lower frequency, and that's why they call this part of it down conversion, because it down converts it in frequency so that you can actually use a lower bandwidth ADC to do all of this extra stuff in digital. So as we saw before, this is almost certainly our ADC down here coupled in to our main Spartan 6 FPGA, because here's the output of it here. As we saw before, it's actually jumped to an inner layer there, as I mentioned before, so it ducks under, so to speak, the ground shield around there with the die-cast shield and everything else, jumps to a lower layer there. So this is the final output of our final filter here, just before the ADC. And there's another TL072 down there. They just love using those on here because, you know, they're only working at, you know, sub 1 megahertz. They're not working particularly fast at all. Maybe they're you know, buffering some sort of low frequency signal or something like that, but clearly we have a couple of RF amps in there. Those are a typical RF amplifier package. I have no idea of the part number, but you know, they're basically you know, supply, ground, input, output. But that's a very typical package for, you know, a low noise amplifier buffer or something like that. We've got another package there which doesn't seem to be lasered off like the other ones. It's almost like it's got some epoxy or something on top of that. I'm not sure what's going on there. And there's our tracking generator output there. There's the big N connector. We've got a multi-stage LC filter there. As you can see, there's no PCB magic filtering happening there. And we've got yet another lasered off chip there. They really don't want you to know what ones they're using in there. They're almost certainly commercial chips. It's not like these are custom ASICs or something, but they're just stopping people reverse engineering this, and it's probably not hard if you spent, you know, a few hours at it to find out what the device is based on the block diagram of A, what it should be, and B, you know, the package type and the number of pins. You can you know, narrow it down in not much time at all. So I'm not sure what that one's doing there. Some obviously looks like some sort of selectable filter. And on the back side of the board, yet another laser marked chip, and there's our Spartan FPGA. So I'm not entirely sure what that's doing in the RF section. Aha, I found our local oscillator. There it is. It's an Analog Devices ADF4106, and that's a 6 gig bandwidth frequency synthesizer, which they're using it as a local oscillator here. So let's have a look here to see if we can follow it. Here's our local oscillator, that Analog Devices part. Let's flip this board around, and it's on the back of here, this section here. So it looks like that's doing some sort of output buffering, and there's probably some filtering in there, and it's outputting through there's like a transmission line going out there. So let's take a look at where that pops through on the other side. No, it's obviously going to an inner layer. So it looks like, where are we? It looks like that pops up there like that. It's going into here. Yeah, so we have local oscillator on the back here, going up here, probably a mixer after some of the input filtering up here, and then our resolution bandwidth filter is the rest of that going out to our ADC over here. Aha, I finally found the main 10 megahertz oscillator. There it is there, and it's in the RF section here. So it's generating both the system clock by the looks of it for all the digital section, as well as of course all the stuff for the RF section. So then it just pops out here, and we've got some additional circuitry over here, and it eventually comes on over to clock all of the digital stuff as well, because there is no local oscillator here, no pun intended, for the DSP processor and the rest of the digital stuff. And if you have a look at the back side of the local oscillator circuitry here, you can see some more PCB components going on. We've got diodes here, and look, it goes through this long controlled impedance trace over to the via stitching over here. Why do they do that? Because that is a controlled impedance component on either side of that. And in this block here, just above the main oscillator down here, I found an Analog Devices AD5449 dual current output DAC with some companion TL072 devices there to convert the current output into voltage. So that's been a relatively quick overview of the DSA815 main board, and it's relatively impressive. I really like it. It's well engineered, and you know, it's only a 1.5 gig spectrum analyzer, but they really seem to have gone to town here, and it's not just some gimmick. That's why the performance of this thing isn't bad, and well, is pretty spectacular for the price actually. And they've done a lot of work integrating this thing into a single board. I really like it because there's nothing else in this product, just this main board and the power supply. And there's the connectors bolted directly on there. Brilliant. I like it. Thumbs up. And there's a quick peek inside the power supply. It's, they're doing all the right things. They've got input protection, they've got input filtering, they're using EEVblog brand capacitors, which aren't too bad at all. They've elasticed a lot of it down. They've got output filtering. Yeah, it's all happening. They've got high voltage isolation slots there. We won't go into it in too much detail because really it's not that interesting, and we've done that in previous videos like the oscilloscope teardown. But yes, it is a good quality. Looks like quite a reliable, or it should be quite a reliable power supply, well engineered. It is Rigol branded there, but yeah, they may have subbed it out to somebody else, but yeah, its model number is LPS SMPS80 version 1.1. And of course the rest of the guts under there, not particularly interested in that at all. It's just a display and a keyboard. Will have some local circuitry on there for the keyboard. Boring as the proverbial bat poo. So there you go, it's back together again, and yeah, that was really interesting. I mean, got our ADC here, and pretty much I think that Spartan 6 FPGA there is probably doing like the all your traditional sweeping functions and whacking it all straight into memory, doing some processing and stuff perhaps. I'm not sure how much of the heavy lifting the Blackfin DSP processor is doing down there. Probably not much. Like in the other Rigols, it's probably just doing some, you know, just your, you know, regular GUI interface type stuff and things like that. So maybe all the grunt work is done inside that Spartan 6, but as I said, that's not a particularly large unit. So, but it's at least handling the ADC input there. So it is doing that, and quite possibly it looks like it's driving out here as well. Like it's generating, like there's all these clocks and control signals and stuff. So it's probably going out here and controlling the you know, the local oscillator and doing all sorts of jazz like that. So who knows? So there you go, the warranty has been voided. Gonski. And let's power this thing up and see if she still works. And it looks like we have a winner, folks. Check it out. There we go. Little spikes from my RF remote here. Beauty. And yeah, that was an interesting look inside the Rigol DSA815. Very well engineered bit of kit, especially for the price. I mean, this is practically the lowest price spectrum analyzer like this on the market by far. Yeah, it's a nicely designed, engineered unit, but that's what we've come to expect from Rigol these days, and they've certainly didn't disappoint. I think it's a winner. So if you want to discuss it, I've almost certainly skipped over stuff and missed stuff and maybe got the odd thing back to front. But the best place to discuss it is over at the EEVblog forum. Catch you next time.